Hello everybody and welcome to the next section of our Rust Recipes series. During this section, we are going to be looking at lifetimes and multi-threading and how we can handle data across multiple threading. During this video, we are going to be looking at lifetimes and making sure we can get our head around them as they are a very new concept in Rust. So I've created a new cargo project called D3 Lifetimes. And here we have our main function, and I'm going to create a new function called makeStr, and this will take an n of some kind, and it will return, for now we'll make it return a pointer to a string. This won't work, but we've got to work out why this won't work. Okay, let's start by just returning a static string, and we'll call that string hello. And it's asking for something here. It's saying the lifetime doesn't make sense. So now we're going to say this is a static str, and this allows us to return it because this guarantees that it will exist for the lifetime of the program. However, what if we wanted to include something in this variable like n? Well, the concatenate doesn't really work, but let's imagine that we really wanted to do something like this. The way to do that is with the format macro. So we'll do hello, and format is a macro, but it acts like a function and it returns a string built of these properties, just like the println macro does. So we now have a result, and we'll put that in a variable. We'll let s equal that. And now we need to choose what we're going to return. Well, let's return a pointer to this string. The error message we're getting at the bottom here is cannot return a reference to a local value s. So s is a string that exists inside this function, but as soon as this function ends, it is going to stop existing. And if we return a pointer to something that no longer exists, we have a problem. People will be trying to reference that pointer like it points to something that matters, but it basically leads to undefined behavior. And we don't want undefined behavior in our program. So instead, we'll change the return type of this function to string. Now, string is actually a built-up, which is kind of in a box. It's on the heap. So I need to clarify the difference between the heap and the stack. The stack are just the variables that exist only while this function is going to exist, and the heap is the memory that is generally available for programs to use. And they have to ask for memory from the heap, so there's a function traditionally in C called malloc that gives you the memory you need. And so if something is on the heap, you need to make sure to free it before you end the program. So string is a box, it acts as a pointer, but when string is dropped, it remembers to drop its content string from memory. And that's what box does. So if ever you see something put in a box, it's saying, I'm just a pointer to something on the heap, but if you drop me, I will drop the thing that's on the heap. Let's look at another example of something that we can do. So we're going to take a pointer of a string. We'll have a function called part, and that's going to take string, and it's going to take a pointer to a str, and it is going to return a pointer to a str. So if the string length is greater than 4, we're going to return the slice, the first 4 characters. But if the string length is not greater than 4, we're just going to return the whole string. And basically, it's just going to take the first 4 characters. So it's only going to be a part of the string that it's taking. So we use s square brackets. This is a way of making a slice, and it works on a slice. We give it a range object, and a range knows how to reach the right parts of the slice it's taking. And this will return a part of that string. This is used in functions like trim and removing white space from the beginning and end kind of functions. But it can't be used for functions that will actually actively return a changed string, because then you need to have something different. You can't just point to the last thing. It is probably the biggest reason that anyone would want to use Rust is getting these memory guarantees that you're not going to accidentally reference memory that doesn't exist, or accidentally try and free the same piece of memory twice, or try and change something that you shouldn't be changing. It's all in the function signature, that the contract that is the function is much clearer for anyone who comes and looks at it and goes, oh, I know what that's going to do. So clear, in fact, that the compiler can make a lot of checks on our behalf. So now we should test our usage of that. We'll create a new variable, a string variable, let s equal, and we'll call makeStr with 7. So we've got a new string value. And now we want to act on maybe a part of that string. So we'll let p equal part, and we have to send a borrowed version of the string. Now, technically an AND str is different to a pointer to a string, but a pointer to a string can easily become an AND str, and Rust compiler knows that happens. It implements something called the deref trait. I'm not going to cover that in much more detail, but you can look that up if you want. Now if we try and push a string to s, so we'll just add the letter p. Okay, we have to make s mutable to be able to do this. So this should put a p on the end of str, but if we look at the error, it says cannot borrow s as mutable because it is also borrowed as mutable. Well, why is it borrowed as mutable? The thing here is that p is referencing s, and Rust knows that. It can see that p has a lifetime connected to s. So as long as p exists, we have a mutable borrow of s. So if we get rid of the s.pushString, everything about this function is correct. It's telling us we don't need to mutate s. But let's say we push string before we make a reference to p. Again, there is no problem with us changing things. But again, we put the reference above and we have an error. The reference below, and that means we don't. So Rust is saying here, you cannot mutate something while something else is borrowing it. So this is really what the part function looks like. So I'm going to add some lifetimes to the part function to show this is what is actually happening. What Rust has done is it has attached a lifetime to p based on the lifetime of s. This is when Rust makes a guess. We haven't given any specific lifetimes, but it said, well, there's a pointer in and a pointer out. The lifetimes have to match, because you can't just create a lifetime out of nothing. We have to declare a lifetime called a, and we'll attach that lifetime, and this is done with an apostrophe a, very commonly a. There's rarely more than 2 lifetimes in a function. And it says these 2 strings have to have the same lifetime. So as long as p exists, we have a pointer to s. So let's talk about another way that we can write these functions. Let's take a function that takes a string, changes it, and returns a different string. When you take a string, not a pointer, if you're not taking a pointer, which the AND is, or a borrow as often it's called in Rust, the ownership of the object becomes part of the function, and that means no one can access it again afterward, unless we specifically return it from the function. So again, let's try something slightly different. We'll do s equals to people, cannot move s. So what this is saying is we want to give the ownership of s to this function, to people. But we can't do that because we're currently borrowing it. So again, if we put that above the borrow, we can, and we'll just put it back into s again. We made it return a string. And so now we'll change our print line to print out both of these values, and you should see that p is the part string, is only the first 4 characters, and s is the hello people string that's been added to. But if we did that the other way around, it just wouldn't compile. And there is one more option that we want to talk about here, and this is a function that takes a mutable value. In fact, this doesn't even need to return anything because it's taking something that is mutable, and again, it's declared in the function. So we can just act on s directly here. So we'll add frogs on our toFrogs function. This is taking a mutable pointer. So now we can call toFrogs, and then we call it borrow it with s, and it's complaining that's mismatched types because actually we need to declare in our function, we know that this is a mutable thing. So we say and mute s. And this again, it just helps people to know that your function is a changing the thing function, and again makes it clearer to the compiler. So now we have the error, we have a borrow, and we're calling a function on a mutable s. And we don't know exactly what frogs does, but we know it changes s, so we can't do it. So we'll run this one more time with things in the right order, and here we go. We've managed to add 7 people frogs. One more thing I do want to talk about is the idea that we can attach lifetimes to objects. So I have this string holder type here. It's going to be something that is going to hold a string. You often want your structs to contain a pointer of some form to something, and maybe that's to point to something that exists elsewhere. You can use a box, as I've mentioned, and you just write box new and put it in, and that way you have an owned pointer to the heap. So And there are very good reasons for doing this. But if you want to point to something else, you'll need to attach a lifetime. So again, at the end of string holder, we put the angle braces, declare the lifetime in the same way as we would declare a generic type. And then we can give it contents that depend on that lifetime. So we'll now make a function, public function toString. So we're going to combine these two strings into a string holder. We'll take S and that will be a pointer to a string. We'll take T and that will be a pointer to a string. And we will return a string holder. We can just write S and T here because they are the same type and the right things. But it's saying lifetime needs to be declared. So let's give our string holder a lifetime and we need to declare that lifetime. And here it's saying explicit lifetime required for the type T because we're using it and putting it together with the string holder. So here we're saying, again, all of these lifetimes have to match. That's what you're saying. And often you do just need to write the same lifetime. So we'll let tog equal, and that's tog for together, the toStrings function, and we'll make two strings here. Yeah, let's send it P, which is already a pointer to a part of a string, and we'll send it a pointer to S. So these two are separate strings. They're kind of related pointers. They have lifetime together already is actually the same lifetime, it's S. So now tog exists, has a lifetime A associated with it. So again, if we try and make any changes to S, this is just not going to work. Well, actually it will work. The compiler won't complain as long as we are not using tog afterwards. But if we need to use tog afterwards, then the compiler will complain. So let's do something with tog. Print line, tog equals, and we'll use question mark here to say we'll use its debug value. This is going to complain because string holder doesn't implement debug, but we can derive debug. And now it's complaining, saying we cannot borrow S as mutable, which is what push string does. It borrows S as mutable. And we can't do that while tog still exists, but we can do it after the last time tog has been used. Finally, let's print out what S looks like now we've added all of these strings to it. And here you go. The final S is hello, 7 people, frogs, anything. Hopefully that's clarified a little bit about how lifetimes work in Rust for you.